In our last video for week 4, we're going to talk about confidence intervals for proportions. We're following our 4-step method, state, plan, do, conclude, and we know that the state step looks the same for everything. Identify what you're given in the problem, identify what you're being asked to find. For the plan step, if you're dealing with proportions, it's a 1 prop z interval, 1 proportion z interval. And in the plan step, you're going to need to find some values related to the problem. If in the problem you're given the number of successes and the sample size, you're going to want to find the sample proportion for success and the sample proportion of failures, p prime and q prime. P prime is x over n. We saw that with binomial problems, successes over sample size. And q prime is its complement. So if p prime was 0.4, q prime is 0.6. If p prime was 0.75, q prime is 0.25. These two things should add up to 1. That's the most common format for proportion questions. Sometimes for proportions, you'll be given the sample proportion and the sample size. And if you're using a TI-84, you're going to need x, which is the number of successes. So in this case, if you're given p prime and n, you need to find x and q prime. Q prime is the same, 1 minus p prime. To find x, you're going to do sample size times sample proportion, n times p prime. We saw that during binomials. And you're going to round it to the nearest whole number. X cannot be a decimal, because x represents a number of people or a number of things. Those come in whole numbers. If you try and give a decimal for x in the calculator, it will throw a tantrum. So make sure you've rounded to the nearest whole number. You'll find your critical value here, just like we did before. And for proportions, it's always the standard normal, because we are approximating the binomial with the normal. There are 2 checks that you should do here that sometimes pop up. In order to use this distribution, we are assuming that n times p prime and n times q prime are both greater than or equal to a lower limit. Some books say 5, some books say 10. 10 is more conservative. I prefer the 10 just because that's what the AP test uses, and I teach AP in addition to this course. But there is a lower limit, and if we're less than that, the normal is not going to be an accurate estimate of the binomial that actually exists here. We are estimating a binomial distribution with a continuous distribution. If this is not true, the normal is not a good fit. It is safe to assume for most questions, particularly in your textbook, that this has been met. On your test, you may be asked about it. This condition should be true. So once you've stated what you're doing, you've found those related values, and you've done your check if you've been asked to, we're ready to go on to the do. We know what our formula looks like. Sample statistic plus or minus critical value times standard error. Critical value is a z-star. Standard error for proportions is square root of pq over n. You're going to substitute those values that you found in there, and then you're going to use a calculator function to find the interval. For proportions, it is not z interval, it's 1 prop z int. And that's option A instead of option 7. So make sure that you're going to the right spot on the calculator, because if you try and use z interval, this information doesn't have prompts for most of it. So it won't fit well together. When we do our conclusion, the conclusions for proportions are almost identical to the conclusions for means. We are blank % confident that the interval from blank to blank captures the true proportion of, and then we write the context of what proportion we were estimating with the interval. My hope is that this will feel familiar because the process is very similar to means. Confidence intervals are confidence intervals. Let's go ahead and do a couple examples so we can get some practice. Our first example says, suppose 250 randomly selected people are surveyed to determine if they own a tablet. Of the 250 surveyed, 98 reported owning the tablet. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of people who own tablets. So first thing I notice, I'm being asked to do a 95% confidence interval for the true proportion. So I know I'm doing a one prop z-int when I get down to the plan stage. For state, I'm just going to list what I'm given in the order I was given it. So 250 people were randomly selected. That's my sample size. Says of those 250, 98 owned a tablet. So x equals 98 people, and I'm going to write down what it is, who owned a tablet. And I'm asked to estimate the true proportion. So P equals proportion of tablet owners. I was also given my confidence level. I was told that that was 95% or 0.95. My next step, 2, is the plan. I'm asked for a proportion. So this is a 1 proportion confidence interval, 1 prop z int. I know my critical value is a z value, so I'm going to do that first. We know 95% is in the middle, 5% cut it in half, 2.5 in each tail, negative z star, positive z star. And we know to get that z star, we're doing an inverse norm command. So we come over to our calculator, second, vars, option 3, 0.025, 0, and 1. And that's 1.959, so 1.96. We also need our sample proportion P prime and our sample proportion for failures Q prime. So I know that P prime is equal to x over n, which is 98 over 250. And I know that Q prime is 1 minus P prime. So we'll pull back up our calculator and we'll do that math really quick. So 98 divided by 250, and we get 0.392. And 1 minus that answer is 608. So from here, we're going to go ahead and pull that formula down for a 1 prop z int. P prime plus or minus critical value times standard error, which for proportions is P prime Q prime over n square root. And then we plug our values in. So 0.392 plus or minus 1.96 times the square root of 0.392 times 0.608 divided by sample size, which was 250. this is another thing we could do by hand, or we go one prop z int on our calculator. So we're going to go stat, tests, we want to go all the way down to a, one prop z int. So the number of successes, x, was 98. Whoops, 98. Our sample size was 250, and our confidence level is 95. And we get a sample proportion, or a population proportion estimate of somewhere between 0.331 and 0.4525 would round up to 3. Our last step, we're going to go ahead and write our sentence. Our conclude step. We are 95% confident that the interval from, and I'm going to state those proportions as percentages because humans generally interpret percentages easier than decimals. So the interval from 33.1% to 45.3% captures the true proportion, and now I'm going to grab from the word problem, the true proportion of people who own tablets. So hopefully that process felt a little bit familiar after having done means in the last video. We're going to do 2 more examples. So our next one says a CBS News New York Times poll found that 329 out of 763 randomly selected adults said they would travel to outer space in their lifetime given the chance. Estimate the true proportion of adults who would like to travel to outer space with 92% confidence. So, I know that I'm being asked to estimate the true proportion of adults, so this is a proportion question, and they use the phrase with 92% confidence, telling me that it's a confidence interval. I'm going to do my state, plan, do, conclude. So I was told X is 329. That's the number of successes. These are people who would travel to outer space. Whoops, that's not how you spell travel. We are told we had a sample size of 763 people. And we're estimating the proportion P of people who would travel to outer space. And I'm going to be lazy because I can. I'm also next to here going to write my confidence level because that was the last thing I was given. And our confidence level is 92% or 0.92. 2, I'm constructing a 1 proportion z interval. I need my critical value. And because I was given x and n, I need p prime, q prime. So confidence interval first. For proportions, it's always z. 92% in the middle. Negative z star, positive z star. That leaves 8% for the tails. Cutting 8 in half, I get 4% for each tail. And I know to get my z star, I'm going to run inverse norm on my calculator. That's not what I wanted to do. There we go. So second vars, option 3, 0.04, 0,1, and I get negative 1.75. So 1.75 for our critical value. We also want p prime, which is x over n. We want q prime, which is 1 minus p prime. So for us, our x is 329 people who want to go to outer space over 763 sampled. So 329 divided by 763. So 0.431. And then 1 minus 0.431 is 0.569. From here, we move to step 3, which is our do step. We know that we want p prime plus or minus critical value times the standard error, which for proportions is p prime times q prime over n all square root. And we're going to fill those values in. So 0.431 plus or minus 1.75 square root 0.431, 0.569, and our sample size was 763. And of course, we do not want to do that by hand, so we go stat tests all the way down to 1 prop z int, and we input our values. So there were 300. Sorry, my calculator is not cooperating today. Stat tests A, there we go. 329 successes out of 763 people with a 92% confidence interval. And calculate gives us 0. And if that were 3998, that's actually going to round to 400. And 4625 is going to round to 463. So for step 4, which I'm going to leave off here because I want to get this video done quickly, we would write our conclusion. We know how that starts. We are 92% confident, blah, 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 that the interval from 40% to 46.3% captures the true proportion of adults who would like to travel to outer space. So we are 92% confident, interval from here to here captures true proportion of adults who would like to travel to outer space. You'll notice that the things in our sentence frames are coming from 3 places: confidence level, interval boundaries that we calculated, a statement of what it is that we were estimating in the problem to begin with. Just like in the last video, we saw that some of these questions are not going to ask for confidence intervals. They're going to ask for sample size. So I want to do just one of those questions to give you a feel for what it looks like. So this example says, a federal report indicated that 27% of children ages 2 to 5 years had a good diet, an increase over previous years. How large a sample is needed to estimate the true proportion of children with good diets within 2% with 95% confidence? So again, I see an estimate of the true proportion, which gives me an idea that this is a proportion question. And it says how large a sample. So I know that while this is a proportion question, it's not interested in an estimate for the proportion as much as it's interested in a sample size. So I'm going to keep that in mind when I get down to step 3. For the state step, it says a federal report indicated that 27% of children ages 2 to 5 years had a good diet, an increase over previous years. So we have an estimate for P. We're estimating that it's 0.27, which means I know that Q, which would be 1 minus that, is estimated to be 0.73, assuming I can do math in my head. They're asking us for a sample size, n equals what? Given that we want to estimate to within 2%. And we've seen that phrasing before. We know that within 2% means margin of error. That's the EBM. So my error bound measurement, my margin of error, is 2%, which is 0.02. And I know my confidence level is 95%, or 0.95. For step 2, this is still a 1 prop z int. I'm working in that universe using formulas that come from that method. And I still need to find the critical value even though I'm given an estimate for P and Q. So we know that's a z. We know we want to be 95% confident. That leaves 5% for the tails. Half of that's 2.5. So we'll go ahead and run inverse norm for that. So 0.02501, and we get 1.96, which we've seen before with a 95% confidence interval for a normal distribution. For 3, I know my margin of error is the second part of the confidence interval formula. So my error bound measure, EBM, for that confidence interval we did up here is just this chunk, the thing after the plus or minus. So z star square root PQ over n. And I want to solve that for n. So let's do some math, shall we? First I'm going to divide by z. So square root of PQ over n equals the error bound over z star. Next, I want to get rid of that square root. I'm going to square this, so we get PQ over N equals EBM, over Z star. I know when I have fractions like this, I can flip both sides. So as long as I flip this fraction over here, NPQ, and I flip this fraction over here, I should be fine. So Z star over EBM. And then to solve for n, I need to multiply by the stuff in the denominator. So multiply both sides by PQ. I get sample size n is PQ Z star over EBM squared. If you are not great with algebra, that is okay. This is not an algebra class. Formulas for sample size can be found at the end of chapter 8 in your textbook. This is an open book test. This is open book homework. There is a formula review at the end of chapter 8. Don't hesitate to use it. I'm going to go ahead and plug in the values we had, because we have values for that above. We know P is 0.27. 0.27. We know Q is 0.73. For our fraction, we know that our z-score was 1.96, and our error bound was 2%, which is 0.02, and that's squared. And I'm going to type it in my calculator exactly as it showed up there. So 0.27 times 0.73, and then in parentheses, 1.96 divided by 0.02 squared. And I get 1,892.9. I'm going to jot that down really quick. So 1892.9. I'm going to zoom out here. I know that I cannot sample 0.9 of a child. That's not great. So for step 4, we need a sample of size 1, 8, 9, and I round it up to 3 to maintain an EBM of 2% at 95% confidence. I'm taking that decimal value for sample size and rounding it up. I always would rather have a larger sample than a smaller. And then just writing a sentence to say what that sample size was for. All right, so that's it for interval estimates for week 4. If you have any questions on the material for this week, don't hesitate to send me an email, drop by office hours on Tuesday or Thursday, or email me to schedule an appointment for a time that works better for you. When I see you next week, we're going to extend what we know about this 4-step method to hypothesis testing. I'll see you then.